Hello? Hello, can you hear me? Hello? Hello? Can you hear me? Hello? I see two people online. Can you hear me?
Yeah, I can hear you.
Oh, okay. Is that Hang?
Yeah, this is Hang. Hi.
Hi, how you doing?
Pretty good. How are you?
Great, thank you. And Harshad just joined. Hi, Harshad.
Hi, I have 5 people with me. We'll be joining in around 2 minutes or so.
Oh, okay, good. Can you hear me fine?
Yeah, I can hear you.
Okay.
But I can't see you though.
Yeah, I'll turn on the video in a second.
Okay.
How about, is that Andrew? Andrew?
No.
Yeah,
79?
What? Email or
Andrew, can you hear me? Hi, Andrew, can you hear me? Hello, Wanting? Hi, Wanting, can you hear me, Wanting? And Priyanka just joined. Hi, Priyanka, can you hear us? Can you speak to see if we can hear you? Yeah, no, we can't hear you, Priyanka. We can't hear you.
Okay. Yeah.
And Scott just joined. Hi, Scott.
This one? Yeah, because he's saying, can you hear me?
Okay, so yeah, I think once we are connected, and then we're gonna hook it up with the HDMI.
You might want to check to see if you can fix your microphone. See if you can choose a different mic input. If you go to the top, there's a gear. If you click the gear, you can check check a different microphone.
Okay. Let's do it that way then.
Hi, if you're not talking or asking a particular question, could you please mute your microphone?
Do we have an HDMI?
No? This one?
Okay. Hi, Preeti. Preeti just joined.
But then you have to connect this one as well.
Where do you put your earphone jack in? Over there?
Yeah.
If it has an HDMI, I think
That's
it
the
does.
password. In using mostly SQL. Just a minute.
Hi, can you all please mute your microphones?
Now to create
Okay, perfect. Yep. Thank you. Let's see. Let's wait a couple more minutes, see if anyone else joins. Let me see if I can share my my screen and you can see. You are screen sharing. Present to everyone. I'm showing this introduction to relational databases. I want to make sure that you can all see this set of slides. Can someone unmute and tell me if you can see these slides? Can everybody see those slides?
No, I actually, well, I think I only see part of it. I mean, part of one slide. It's getting really weird.
Do you see it says Introduction to Relational Databases? Dr.
Nope.
Jose?
It's like there's a blank line that's like,
Do you
yeah,
see
my screen is really weird.
Do you see agenda 1, 2, 3, 4, 5, 6, 7?
No, let me probably do it again. Let me see if I can fix this part.
Maybe you could put it full screen.
I'm using yeah, I'm using it full screen. Let me try it again.
Somebody has a sound. I think it was Hal. I just muted Hal. You were getting into a feedback. Anyway, let's see. I'm showing the agenda here. Let me see if I can make it bigger. Zoom in. No, that's not it. I'm gonna show it a little bigger. 2 viewers. Okay. All right. I'm gonna start here talking about this agenda. Let me this is somewhat of a repeat of what we talked about a little bit last week on Wednesday last week. And I see that some of you already are some of the same people that came. Let me turn on my video just so you can meet me. This is me. Hello. Nice to meet you. And we're really going to meet next Thursday to go over a lot of the material that we're going to need for the assignments and the projects. And so today is mostly an introductory class, a little bit about, in general, what the topics we're going to be talking about throughout the course, and talking a little bit about the assignments and the various project-based assignments that we're going to be displaying later on in Piazza. Also, has everybody received an invitation to Piazza? Everybody should be able to see to view Piazza, and the assignment, the link to the first assignment is there. Also, the links to all these slides are there as well. We're only going to be using Blackboard for you being able to submit your assignments and to receive grades. Okay. All the discussions, any questions you might have, please use Piazza. And we also have identified a TA that will be physically there in the Seattle office that you should be able to coordinate with him. What will be the best times for him to hold his office hours? Okay. Now I believe most of you are at home right now, but on Thursday, my understanding is that graduate international students need to be physically in the building for, I guess it's a visa requirement. I wasn't aware of that. You know, as far as I'm concerned, you know, it's fine for you to just stay home and in the comfort of your house. I mean, as far as I'm concerned, but apparently there's some visa requirements for you to be physically in the Seattle office. Those that don't need to be there, I encourage you to be there anyway, to mingle with the rest of the students and have questions for the TA that might be there as well, and also coordinate for your projects. There's a project due at the end of the semester, and we encourage you to take use groups of 2 or 3 students. You could be all by yourself, but if larger groups, you know, 2 or 3 would be great. The first half of the course is mostly how to use SQL to be able to manage databases, you know, create tables, create triggers, create store procedures, create authorization and authentication of databases, indexes, and so on and so forth. Some theory on how to best design databases, to avoid redundancy in the database, because as we'll see, redundancy breeds inconsistency in the database, and we'll talk about that, and that's part of the first assignment. And a lot of the things that the topics that we'll need for the first assignment we'll cover on Thursday. Also, I put a link to the previous presentation that we had on Wednesday. I encourage you to look at that as well. It's mostly me talking about, in general, a very, very broad coverage of the material and the topics that we're going to cover in this class, and where do we fit in specifically, these slides that we're going to talk about, specifically how does it fit in that broader sense. The first half, I was saying, is very theoretical. Quite a bit of slides. The second half is more hands-on, more practical. There's a lot of coding. You're going to be doing a lot of coding in this class, which culminates with a project at the end of the semester. We're going to be using Java mostly to implement applications that use databases that access. You have a question?
I'm sorry to interrupt you.
Yes.
But on the other end, and there's drop this and join it again.
I'm sorry, I can't hear you. Say again.
There's a lot of noise and video lag, so I can join again.
You're gonna drop and join again?
Yeah.
All right, go ahead, try it. Perhaps if we all close our video, and so that we don't have lag on the video, and only use audio. Only if you need to, make some gestures with your hand, perhaps. But let's minimize the broadband that we need by closing all our videos. So let me do that. See if the network moves. Okay. How about you, wanting? Maybe you want to close your video. And also, how? Maybe you want to close your video. Thank you. All right. Let's see if it's any better. Again, if you need to interrupt, please feel free to interrupt. Anyway, so let me just cover the very basics of this course. First of all, in general, what do we mean by a database? So basically, of data in some structured manner, format, can be considered to be a database. And it could be a flat file with perhaps a record per line, and you can decide that a record is delimited by perhaps a new line, a character return, and then each field, perhaps it's structured in such a way that uses vertical bars or commas or tabs or whatnot. I mean, you could, any structured file that collects data in some substructure way, it can be considered a database, right? And then, but they all share certain things in common, right? What we want to be able to do is to make it easy for us to access that data, right? And I mean, you could write programs in any particular language that will open up the file and parse it and extract the data in the fields, and after doing that several times, you find that there are patterns, right? Things that you find yourself doing all the time, right? You find yourself always opening the file and just reading each line one at a time and parsing out all the different fields, and it gets and then perhaps comparing those fields against a particular predicate, a particular condition that it meets, and then you you collect all those records, all those lines that meet your particular criteria, and then you return from that function that you wrote in Java or C#, the collection of records that meet that particular criteria, and then you might find yourself that if you do this several times, you find says that you might say, well, can't we write a generic technique to do this, right? And that's can I create some high level language that would allow me to parameterize such a high level function, and that's basically what a select statement does in SQL. Right? And SQL basically is it's an abstraction, right? It's a way of thinking on how to collect data into some structured format that then provides a high level way that we can then access that data, right? And SQL is just one particular way that the industry has agreed upon on how to think about the database. We're going to be using a particular database throughout the semester. You'll see this repeat several times. This is the database that the book uses. It's called the University Database, we're going to see these types of records over and over throughout the semester. We'll have a table that is called the student table, the department table, the course table section, enrollment table, and each one's going to have attributes such as, for instance, the SID. The student will have SID, the name, the graduation year, the major ID. Then the department is going to have department ID, department name. Then the course is going to have a course ID, title, department ID, and so on and so forth. So yeah, so this is an example, a running example that's going to run throughout the semester. These are also examples. I hope you can all see the slides here. I'm assuming you can. These are example records inside of those tables. So you can see the student records here that has 9 students, and you have the departments, 3 departments.
Hey, sorry, I have a quick question. Are you sharing
Yes.
the screen now, or are you just talking?
No, you should be able to see. You should be able to see the tables. Do you not see the tables?
No, and also Scott just texted me he couldn't see it either, so we both couldn't see it.
Okay.
I
Thank
only
you.
saw your picture.
Okay. How about? Let me see.
Because I just dropped and rejoined, and I still couldn't see the screen. I don't know what happens.
All right. Let me see. Just a second. How about? Don't go away. Just stay there for a second. All right. How about now? Do you see?
It's still, well, I think I'm supposed to see the agenda. It's just that the screen is a bit weird, but yeah, I can see something now.
What about now? It says, what is the database? Do you see that?
Yeah.
And then it
Yeah, I
says
can
University
see
Database. Can you see that?
Yeah, I can see it.
Okay.
Cool, thanks.
All right, these are the records. I hope everybody else can see it as well. Please, if you don't see something, I might not be able to read your text. If you're texting me, please interrupt me and immediately, and let me know if you could see or not see something. Yeah. So as I was saying, these are example 5 tables that we're gonna use over and over throughout the course. And there's the same example that you will find in the book, where there are 9 students, 3 departments, 6 courses, 5 sections, and 4 enrollment and 6 enrollments. Notice that the students have an SID which uniquely identifies each one of the records. That's a common theme that we're going to be talking about perhaps a little later. That records need to somehow represent some uniqueness feature that uniquely identifies it in the overall set of data. And notice that it has at the end the major ID. The major ID, notice those numbers 10, 20, 10, 20, 30, 20. Those are actually foreign keys, right, that refer to other records in the throughout the database. In this particular case, it's referring to records in the department table. If you notice in the department table, you have DID 10, 20, 30. So, for instance, the student record 1, Joe, 2004, major ID 10, it's saying that Joe is in the department number 10 in computer science. Now, one might say, well, why don't we have all this? Instead of having it spread out over 5 different tables, why don't we have it all spread out in a single table, right? It could be one huge table, and then you would have the name of the department repeated several times in that huge table, right? You would have maybe one huge student table where you have all the students, and then the department ID, instead of having a separate department table, you might have it repeated several times in the student table. Also, if you have the course table, also that too could be repeated several times in that big table. And what you might start seeing is that a lot of the data is being repeated over and over across all these records. And we usually tend to shy away from that kind of representation where we have one huge tables with a lot of data repeated several times. And usually the reason is that we want to avoid the redundancy, right, where data is repeated many times throughout the database. Because what if you change one of the field values in one of the records, but it's supposed to be changed everywhere, right? What if I change the name of the department from comp sci to computer science, right? But if that value is repeated over and over in many records, right, I would have to be either responsible to make sure that it changes everywhere, or run the risk of inconsistency, right? That some records it's spelled one, the department name is spelled one way, and in other records it's spelled some other way. So we usually say that the redundancy breeds inconsistency. So what we do instead of repeating computer science over and over and with this huge table, what we do is that we split it up into several tables. So we have a dedicated department table where the name of the department only appears once, right? So what that allows us to do is avoid redundancy, avoid inconsistency. And then so what we end up is with many different little tables that ensure that the data is only captured once. Now, obviously, this is great. We usually refer to this task of going from huge tables to smaller tables. We usually refer to that as normalizing. It's normal. We're normalizing the database. We're breaking it up into its smaller pieces. And usually it's because we want to avoid redundancy. Now, this is all great. It avoids redundancy, avoids inconsistency, but it inadvertently introduces problems for when you're going to retrieve the data, right? Because when you want to retrieve the data, usually if you want to retrieve the data for the student, not only do you want the student information, but you might also want the courses that the student have taken, with the department name where they're currently enrolled in. You might want to know the sections and the grades that they've taken. So when you want to consume the data, you really want the joining of all this data that has been spread over across many tables. And that introduces a problem in performance, that you need to now reconstruct that data from the various tables that have been split into, right? And that is cost foreign links, foreign references onto the individual records, and that usually is an expense, right? You need to iterate over one table, and then nested iterate over other tables, and that creates a lot of time. A lot of time that you have to spend iterating over these things. Anyway, so we say that the art or the technique of splitting and deciding what the tables look like and what fields they're going to have, and if they're going to have foreign keys, primary keys, and whatnot, we call that design the database, right? So over here we say deciding all these tables. We say it's designing the database. Oops, sorry. Now, the database system is again, it's an abstraction of what the underlying way that we're representing the data. We're creating an abstraction over that internally in the file system. The data might actually be stored in a binary format. But the database abstracts all that, providing us with a model of the data in terms of tables, right, and records that refer to one another. And the database system is the software that manages all these tables, all these records, and it provides certain aspects or attributes. We say that the database systems, and they need to be persistent. That if ever the machine where the database is being hosted shuts down, the database is still going to be there. If the database, if the machine starts up again, right? It needs to be able to store large amounts of data that multiple people needs to be able to access it simultaneously without inconsistency, right? If many people are trying to access it concurrently, you need to deal with issues such as users modifying data while some other people are trying to read it, right? And that might be a problem if data is being shared and they're simultaneously being written to or read from, right? Also, it needs to be accurate, right? This goes back to the fact that we need to normalize our data to avoid inconsistencies, right? It needs to be usable, so it needs to provide some kind of very easy interface that allows us to retrieve the data, enter the data, right? Also, we have the dedicated users that administrate the data and make sure that the database is in a healthy state, right? That now again, how might we store the data underneath? Is it a text file with tabs and new lines? Is it a single file? Is it a multiple files split up into many different files? That is really what we call the physical model, right? How is it physically stored in the file system? And we're not going to be too interested. We're not going to be interested too much on that aspect and how is it physically stored on the file system. We're more interested in a little bit on how is this abstracted at the high level going through SQL. Now, underneath, the database might decide that to split the data into many different files. It might even create auxiliary files that to be able to increase the performance of retrieving the data through auxiliary files called index files that allow you to very quickly find the data when you start joining these tables together. We call them the indices. We'll come back to that a little later. Multiple user access, right? You need to make sure that if you have several people accessing the database at the same time, that you don't allow multiple users writing or trying to manipulate the data at the same time. It might be okay to allow multiple users to read the data, since it doesn't matter how many people read it; they're all going to be reading the same thing. But the problem is, what happens if someone is reading it? Would you allow anyone else to change that data, right? You would disallow that, right? Well, how do we isolate these users from each other to avoid inconsistency, right? What happens if I'm looking at the balance and while I am depositing money into my account, my wife is also withdrawing, right? What would be the problems of updating the data and making sure that the resulting balance is correct, right? So we have to, the database needs to be able to identify these conflicting and often ambiguous and often contradictory commands, right, to update a database. It needs to be able to sequence, right, and serialize these commands to make sure that they're not stepping on each other. So we'll talk about that. The way that it uses transactions to create atomic access to the data. Right. So yeah. So transactional updates, right? For instance, we have to obviously know that we're not the only users using the database. Just like in multi-threaded environments where you can have multiple threads running through the same code, trying to modify a shared resource. Usually what you do is you create mutual exclusive semaphores or monitors, right? That only allow one thread to go in at any one time, right? And what you do is you serialize the access to that shared resource. So transactions is the mechanism by which we can achieve the same kind of behavior in a database. We also need to be able to allow the right people to touch the database, right? We can't allow just anyone to log in and be able to access, read, or manipulate data. We need to first authenticate them, see that, make sure that they are who they say they are. And once we know who they are, we need to be able to then specify what kind of privileges does that person have. Can they view this data? Can they modify this data, right? So we'll certainly spend a lecture talking about how to create these authentication and authorization. Memory management. The database also needs to be responsive, right? We need to be able to respond quickly to queries, and certainly we have certain limits on how much data can a particular machine hold at any one time in RAM, right? As opposed to how much data can hold perhaps in hard drive. Now, hard drive is several orders of magnitude slower than RAM. So the database has to be able to manage the ability of caching as much as possible in the local RAM without having to go to the file system, since it's sometimes hundreds of thousands of times slower to go to the file system, and so the database needs to keep track of what should it to try to kind of be like some kind of a predictor on what next thing you might want, right, and be able to prefetch things and cache them in RAM so that it can more quickly answer your queries, right? So yeah, that's definitely memory management. Now, right, so throughout the course we're going to be talking about different types of data models, right? At the lowest level, the data model is basically just a file system. The file system has a particular way of storing its data. Basically, it's either some kind of binary format, or as we'll see later, it might also be just plain old text, a text file, right? It could be just plain old XML or JSON or just binary in the native file system, and that on itself is a data model, right? How it represents that particular data in the file system natively. Now above that, we create an abstraction of that file system, and we're going to be looking at a lot at what we call the relational data model. We're going to be spending quite a lot of time talking about the relational data model, which is what I presented earlier, right? Where you have several tables, each table having several records, and these records related to other records in other tables, right? And that relationship, that when you say that a particular record in one table is related to other records in other table, is what gives a name to the relational data model. The relational comes from the fact that you have these records that are unique in their own tables, but are related to one another, right? And together, right, these relationships, these records, is what builds what we call the relational data model. So you'll hear me say that quite often. What is we're creating the data, the relational data model, and basically means, we're creating these tables, we're creating the fields and the attributes in these tables, all the data types that make up those tables, the schema, right, and what we're going to refer to it as the relational data model. There are other data models which we're going to be considering. We're going to be considering the object data model, right? We're going to be considering the hierarchical data model, the graph data model. Those are all alternative data models that we're going to be looking at later on. The object data model, I'm sure you're all familiar with it already. If you've used any object-oriented programming language, you've been using the object data model, right? You represent the data, as a collection of objects that might have that would exist, typically would exist only in RAM as the program executes. Yes. And then each one might have pointers or references to other objects, right? Or one might have as an attribute of one of the objects, it might be an array of other objects or instances of other objects, or it might have a list of other objects or links, right, to other objects, maybe next or previous, or links to children and then siblings, and that creates what we're going to call the object data model. We'll come back to these alternative data models later on. Let's see. So as a file system, and if we're talking about the file system, the native file system, again, it could be just a plain old text file. Like, for instance, here in this slide, we say that, like, students.csv, right? So the students.csv would be an example on a physical file, right, that has a particular way of representing data and representing records, right? One record per line, each field, delimited by commas, right? And that's a very primitive way of representing data. And one way that you might consider accessing the data is to perhaps write something like this, right? In Java, maybe you write up a method that's saying, get the students from 1997, that opens up the file, reads each one of the lines in the file system, it splits it by commas into an array of strings, and then iterates over the array of strings, looking for a particular element. If it's equal to 1997, that's our predicate, right? That's the criteria by which we're filtering. And if it finds any graduation year that it's equal to 1997, it adds it to a list of results of a result set, right? And iterates. This is scanning the entire file, right? This is scanning the entire file system, the entire file, looking for the records, a subset of records that meet this criteria, and then it returns a result set, right? Now, you might be writing lots of these, right? If you're going directly to the file system, if you're using the physical data model, right? Here we're using the physical data model. After writing lots of these, you're going to find a pattern, right? That you're always doing the same thing, right? You're always creating these array lists. You're always reading you're always scanning the entire file. You're looking for a particular predicate, adding it to a result set. It's always the same thing, right? And what SQL gives you says, well, you know what? Instead of you writing these for loops that iterate over files, why not create a high-level language that allows you to do the same thing? And here it is. Here we have at the bottom of the slide, it says, select the names of the students where graduation year is equal to 1997, right? So that one line of SQL is equivalent, right, to all these lines in Java, right? But really, this is what's happening underneath, right? Underneath, really, this is what's happening, right? Obviously, there's a lot of optimizations that the database systems can make, but really, at some point, you need to scan the file and looking for this predicate. And what the conceptual model, right? What the relational model is one of many conceptual models on there's an abstraction, right, an idea on how we want to think about this data, regardless on how underneath the file system represents the actual data, right? Conceptually, we're going to think of the data being represented as tables, records, and fields, right? And again, this is just an idea, a concept, right? It's not really stored that way in the physical model. It's only an idea on how we want to think about the data. Again, there were other types of data models that we'll come back to later: graph-based model, object-oriented models, hierarchical models. And we want the database to make us, provide a kind of layers of independence, right? We don't want to really think about the physical data model. We want to be independent on how the data is really stored in the file system. We want to only work in the logical level, right, at the conceptual level. And it means all these different tables relating to one another, and that's where we're going to spend most of our time, the first half of this course, right?
There's an additional way of looking at the database, which we call external schemas, which I mean, once we've split the data into all these various tables, we might want to come back and provide a higher level way of looking at the data, which might be a little more convenient, right? If we consider the conceptual schema where we split the data into students, enrollment. Here's the third line in this slide. It was we've the conceptual schema here in the middle of the slide is abstracting the physical schema down below, right? The actual file system down below. We provide a conceptual model that things are being represented as a table student, the table enrollment, and the table section. Now, this might be good as a means of storing the data, but it might be a very inconvenient way of how to consume the data. So we might provide a third level of abstraction called what we sometimes refer to as the external schema, where we provide views, right? Or we provide prepared views that do collections or joins several of these tables down below into more convenient ways of consuming the data, right? For instance, we might create a virtual or view into the conceptual schema, a virtual table called student info, and the student info collects information about the student. From the student table, it might collect information about their enrollment in a particular section, and maybe the grade that they got. So the student info is a virtual representation of the student information that might be collections of several records from different tables, right? It's just a more convenient way for the deans, for instance, for the dean's office, is a much more convenient way of consuming the data, right? And you might have different views into the same conceptual schema. We'll come back to this a little later. We'll see how to implement these using views. Anyway, I think I'm going to leave it here for now. I just wanted to make sure that we were all on board, that we were all able to see the Google Hangout, and just give you a brief introduction to what the course is about. The Piazza, I believe all of you have access to Piazza, and the first assignment. I'll go over the first assignment again on Thursday. And really the topics that we'll need to do the first assignment we won't cover Thursday. So you're not behind. We're going to be caught up together on Thursday. I'll do it first for section 2, and then I'll do an encore for section 3. So you'll probably get a more polished version of the presentation. Anyway, anybody has a questions? Any questions, please? No questions? All right. All right. So I'm going to leave it here. Remember, the Piazza is where we're going to do all our questions, all our forms. If you have general questions about assignments, about the course in general, please make those questions in Piazza. If you have anything that is more specific, that I have something more personal, then feel free to email me. But please try to avoid using email, my email. Instead of, if you have questions about the course, use Piazza instead. The first assignment is due September 23rd. We might need to extend it if again, because there were some problems at the beginning of the semester with the instructor that was supposed to take this section. I'm trying to catch up everybody, 2 different sections into one. What else? Also, remember, make sure that you have access to NU Online, the Blackboard that we're using. If you don't have access, please ask me in Piazza, and I'll make sure that you have access there. And we're going to be using that so you can submit your assignment and for grade. But discussion boards or things like that, please use Piazza instead. Okay. All right. Anything else? Nothing else? All right then. I guess I'll hang up then, and I'll make this available. I'll send a link to the class so that you can review this session sometime later. All right. I hope everybody is able to hear me.
Yeah.
Okay. All right then. Thank you everyone.
Thank
Good
you.
night. Okay. Good night. Good night, everybody. Bye bye.